Good morning. We will continue our discussion on feedback amplifier. So, in last two classes we have discussed about negative feedback, positive feedback and fourth type of feedback amplifier, right. So, in details we have discussed voltage amplifier. So, if we go through a quick recap, we know the advantages of negative feedback. So, what are the advantages of negative feedback? We know that gain is reduced, but stability is increased and input output impedance relationship also changed, right, and we saw that it is in favor. For example, voltage amplifier input impedance is increased due to negative feedback and output impedance is decreased. So, for other type of amplifier we will be watching the same phenomenon. So, these are the characteristics. One is gain is reduced, another is sensitivity is reduced, which is also in the advantage. It reduces the distortion or noise, effect of noise. It controls the input and output impedance, noise already we discussed. Bandwidth, we also saw that bandwidth is increased, although gain is reduced, but frequency bandwidth is increased. So, that is another advantage also. Stability is another advantage. So, this is feedback transconductance amplifier, okay. Feedback transconductance. So, what is your output? Transconductance. Output is current, right. Input should be voltage. That is our transconductance del I by del V, right. So, you see, if we want to sample output current, so what are the different naming topology? One is transconductance amplifier, another is output side it is current sampling, input side it is voltage mixing, right. So, another naming topology is voltage mixing, current sampling. And can you see the connections? What are the connections? If you want to flow the same current, the connection should be in series. So, this is in series, so that same current flows, right. If it is in series, same loop current will flow, and if you want to add or subtract voltage, that should be also in series. So, this is series feedback amplifier, okay. So, when you take a moment to analyze, to think, okay. First you ask the questions, what is the meaning of transconductance? So, you will understand that the output side it must be current sampling, right, current sampling, and at input side it must be voltage mixing, okay. So, one name, two name, and if current I want to sample, that must be in series, right. If it is in a loop, then only same current will flow. If it is in parallel, then different current will flow, right. So, it should be in series, and at the input what we are doing? We are subtracting the voltage, right. Negative feedback means source voltage minus the feedback voltage. So, you see this is minus the feedback voltage, minus Vf. So, if I want to subtract, this should be also in series. So, this is an example of series negative feedback amplifier, clear. So, this is our main amplifier and this is our feedback amplifier, feedback element also you can say. So, again how we will draw the detailed circuit? Input amplifier should have a input resistance, that could be infinite, but for the moment we are drawing that, okay. It should have a voltage gain, it should have a output resistance. Now, as this output side is in current, we draw this is in parallel, okay. We draw that amplifier like an current amplifier, okay. Now, in the feedback circuit, input impedance we are not considering, and we are just considering a beta gain factor, only a gain factor. So, what it is actually doing, the current I 0 that is coming, it is taking a portion of that, that is beta I 0. So, you can say that this feedback element, its gain is beta. My input to the feedback element is I, so my output is beta I, right. So, this beta is converting this to a voltage. So, this beta is kind of a R, right, I into R is equal to V. So, this I is converted to V by this beta. So, you can understand for this example, this is a resistive element, this feedback element is a resistive element, right, and this Vf is subtracted with Vs and we get the our input voltage like Vs minus Vf. Okay. So, now can you tell me, gain we already know, closed loop gain should be reduced by A by 1 plus A beta, that we already discussed, right. Now, in this series my input impedance is larger. Okay. Next, if we discuss current amplifier, so what should be my input side and output side? Input side should be current, output side should be current, right. So, output side we already discussed, if we want to flow the same current, this is current sampling, current sampling. So, if you want to flow the same current, it should be in series. At the input side is also current, and if you want to add or subtract current, this should be also, this is in shunt. Okay. So, this is shunt series negative feedback amplifier. So, you just take a moment and think logically, then you can arrive at the all these connections. So, do not get confused or do not try to remember, you just think logically and you will arrive at the connection diagram. So, this is current mixing, current sampling, okay, done. This is shunt series feedback topology, yes, we also arrived to the same decision. And here this is a current amplifier, right. So, its input output relation should be just opposite to the voltage amplifier. So, my input resistance is decreased, output resistance is increased because of negative feedback. Why this is happening? Because we are using negative feedback. Okay. We did the details analysis in voltage amplifier. So, we are not going into details, but on the same way we can do this also. So, let us check one example in this circuit. So, you see in this output path, this output current I 0 is flowing. So, what we are doing? This is our input source Is that is flowing through the source terminal of this Q1 MOSFET, and a portion, these are parallel connections, right. Whenever there is a branching, this is a parallel connection for the current, two current path is flowing. So, you can say that this is shunt, right. Current can flow in this direction, current can flow in this direction. So, this IF is a portion of I 0. So, this branching, this ratio will give me my beta, a fraction of current will flow, right. So, output side we are sampling current, input side also source is input current and feedback is also current. So, this is shunt series feedback topology or current amplifier topology. Next example is transconductance, we already discussed, right. So, let us just discuss the circuit. Okay. So, input side we all know it is voltage and output side it should be current. So, you see this is an amplifier, right. So, this is positive voltage Vs and this is the negative voltage Vf, and we subtract them, and that is Vi, right. So, input side it is voltage. So, input side it is voltage. Output side what is happening? Whatever the output voltage, that is causing a current I0 to flow, right. If you give a fixed VGS, a fixed current will flow, right. This is a PMOS, PMOSFET, and if my gate to source voltage is fixed, my current will be also fixed, right. So, output side is a current, okay. Input side is voltage, output side is current. So, we are sampling current. This current is converted by this resistance, right. This current flows through this resistance RF. So, a voltage Vf will generate. That Vf we are subtracting. So, output side it is current sampling, input side it is voltage mixing, right. Let us see the second circuit. Second circuit is also similar circuit. This op amp is replaced by this amplifier. Can you tell me what kind of amplifier is this? This first stage Q1, RD Q1. Output you are taking from drain terminal. Input is given to the gate. This is common source. This is direct common source or something else. You see there is a resistance in the source terminal. So, this is source degenerated common source amplifier, no doubt. I have a source degenerated resistance. So, this is a source degenerated common source amplifier. Okay. So, this voltage is going to this, and again some current will flow. That current is converted to voltage by this resistance, and that is coming as a feedback. Now, you can say that why that feedback or how the feedback, we already discussed this in, this is input and this is feedback. So, this will act as a Vf and this is Vs. So, this is my Vi, clear. We already discussed this kind of negative feedback in the source degenerated common source amplifier, right, common emitter amplifier. How the feedback is happening? Because this is my input voltage and this voltage I am subtracting. So, this is my Vi, just like that Vi, na. What is Vi? Vs minus Vf, same thing is happening. What is Vs? My gate voltage. My input voltage is VGS. So, Vg is one term, Vs is another term. So, Vs I am making equal to Vf, Vg I am making equal to Vs, and Vgs I am making equal to Vi. Next is what remains, we already know, current amplifier done, voltage amplifier done in details, transconductance we discussed, remaining part is trans resistance. Output should be, you remember R is equal to V by I. So, my output is equal to voltage, input is equal to current. Okay. So, what you are mixing? Current you are mixing. What you are sampling? If you want to flow same current, series. So, you want to add or subtract. So, this should be mixing, it is in shunt. Output you want to sample voltage. In which connection same voltage? Shunt. Which one was series? Transconductance. So, when it is V and I, then only there is a possibility that both sides should be same, right. So, transconductance series and trans resistance shunt. So, all the naming clear. First one is trans resistance means V by I. So, output is voltage sampling, input is current mixing, right. Next is you come to decision that if I want to mix current, it should be in shunt. If I want to sample voltage, it is also in shunt. Let us take a quick example. Let us see this circuit. My input source is current source. So, input is I, output is voltage. So, this is V by I. So, this is trans resistance, right. So, this current is converted to this voltage by which element? This element. So, V 0 is equal to I into R f, right. Sign we have to check, okay. But the concept mod value is V is equal to I into R. So, you understand that input is current, output is voltage. So, one resistive element should be there in the feedback path. Same way we can analyze this circuit also. Source is a current, okay. Source is a current. So, this branching is happening. So, IF, this feedback is also current, right, and this current is converted to this output voltage by this resistance RF. Okay. Same, this circuit and this circuit same, only MOS and BJT. Okay. So, the concept of all these three is same. I current is flowing, we are converting this to the voltage by a feedback resistance. So, we can also calculate the relationship of input and output impedance depending on this. So, can you tell me what will happen to the RI and RO? Take a moment and think and then tell. See, whenever you are in confusion, you can take example of a voltage amplifier or current amplifier. Current amplifier, what is your output resistance is increased, right, and input resistance is decreased. Okay, we will check this in the table. Okay, final summary table we will check it. So, this is a summary table. This is voltage amplifier series shunt. My input impedance is increased, output impedance is decreased, and this is trans resistance shunt. Input impedance is decreased, output impedance is decreased. Current shunt series, input impedance is decreased, output impedance increased. This is series, so both are increased. Okay. So, the moment you get confused, you get back to the one you have done in details and try to analyze. So, this is a summary of all the feedback amplifier. We can use this negative feedback to design 4 type of amplifiers. By nature, we can have our output could be in voltage, input could be in voltage, output could be in current, input could be in current, output could be in current, input could be in voltage, and output could be in voltage and input could be in current. So, these 4 possibilities we are having, right, and we will also see that what are the feedback topology. Then we will see that if we use the negative feedback, how my input and output impedance are changed, and we will see that negative feedback is actually helping us to change this input and output impedance such a way that it works as a better amplifier. These are few examples. This example we will do in tutorial classes in details. So, for trans resistance, we can calculate the input and output impedance and can show that they are both decreased. This is one example that we will do in tutorial class. So, I am just quickly let me quickly explain this. So, one problem is given, a feedback transconductance amplifier is given. So, what we will do, we will try to analyze different portions, different part. So, this is our feedback portion. Okay. this RF is converting this I to a voltage V. Okay. So, this RF is the feedback element, right. In this portions we have replaced this amplifier with its 2-port network. Okay. Do not get confused by this big circuit, step by step if you analyze you can understand. So, what is there? The input impedance is RID, RID is the differential input impedance, and this connections is connected with this RF. So, this is my input side, this is going through the internal resistance and RF. So, same thing is drawn, right, and this main amplifier has a gain of A. So, this A is dependent on VID, this VID is this differential voltage. So, A into VID, right, and this will have a output resistance. Generally we consider this as 0, but if some value is given we can consider a, right, and this point should be connected to this circuit. What is this circuit? Again I can replace this MOSFET with its equivalent H hybrid pi network, right. So, input impedance is having large impedance and this has a transconductance, right. Output is a current. So, what is the current? GM VGS, right, and it should have a parallel resistance RO, that RO we are drawn, and next this circuit is fixed. Okay. So, whatever we are doing, we all have done this before, just combining them. We have done the 2-port network of BJT and MOSFET, that is also added with another amplifier that we have done in the first chapter, right, amplifier section. So, that if we structure this step by step, then it will become easy. So, we discussed about basic feedback amplifier and their input and output impedance. Now, this RS we can have a source resistance, this we can have a input impedance, this we can have the output impedance of this basic amplifier, and this is the load resistance. Okay. Step by step we will consider. First we will start with not considering them, then slowly we will put them, then we will have the complete circuit. Complete circuit like considering the source resistance, load resistance and the its internal impedance, its internal output impedance and its internal impedance. So, roughly what we can see, that if we use feedback, this is my response, and if we consider that our loop gain is very large, this we can replace with, okay. So, this is the main concept of all the feedback amplifier. You think of op amp, what we are doing? We are considering this A is very large. Why we are doing so? So that when we multiply this with your feedback element, this must be much greater than 1. So that when we are thinking of say one feedback circuit, right, our gain is only dependent on, in negative inverting amplifier what is your gain? Minus R2 by R1. In non-inverting amplifier your gain is 1 plus R2 by R1. Is there anything like A, any expression of A? No, we are neglecting that. How? Because of this interesting phenomena that we call as negative feedback. So, what is our open loop gain? very large, but we are not utilizing that for gain, we are utilizing so that our closed loop gain is well defined. That infinite gain is not helping you as an amplifier, right. If you give a sine wave, it will give you a square wave as an output. So, it is not linearity is not maintained, right. The shape is totally changed because it has infinite gain, but that property is helping in some other way. Which condition? This condition, and so that your gain, what you are actually doing, your desensitivity, the sensitivity of this op amp is reduced, right. Dependency on the technology parameter like the threshold voltage, transconductance, beta, all those technology parameter that can change with time and temperature. Okay. So, we are getting rid of their dependency, and now our gain is dependent on some resistance ratio. So, even if temperature is changing, my ratio will be constant. So, I am having a fixed, okay, understood. This is the main advantage, right. So, these are all written and we already discussed this in. So, this is the summary. So, this is how we find the loop gain. Okay. When a circuit is given, if you want to find the loop gain, you have to break the loop. Okay. If a continuous connection is given, you can't calculate the loop gain. Then what you can do? You can break a portion and put a source and then find the output. So, what we are doing? As if this is a loop, right. So, we do not know where to start. So, what we are doing? We are breaking at this point, we are adding a voltage source V and we are finding a output voltage V 0. Okay. So, we are giving a test voltage V t and we are finding the output voltage. So, this will give us a loop gain A into beta actually. Okay. This loop gain is having the effect of A also, beta also. Okay. So, what we are doing? We are conceptually what we are doing? We are breaking it, putting a source and then checking the output voltage. If it is a current, we will do the same. We will put a current source, we will sort the output and find the short circuit output current. If it is a voltage source, we will add a test voltage, we will make the output open and check the output open circuit voltage, right. So, 3 steps are there. One is adding a test voltage, adding a resistance, finding the voltage. Here adding a voltage source, keeping the output open, finding the open circuit voltage. Adding a test current, sorting the output, find the short circuiting output current. Okay. So, these are the way to. So, physically, so breaking the loop means not physically breaking the loop, conceptually we are doing that. Okay. Now, let us discuss little bit about stability. Okay. This stability you will be learning in details in control theory classes. So, let us consider that you have a, this axis is your real axis sigma, termed as sigma, and this is your imaginary plane termed as a j omega. So, 2 axes, x plane and y plane. X plane is termed as a sigma, y plane is termed as a j omega, right. Now, suppose I have a point here. So, what is the value of this? Say sigma 1. I have a point here. What could be the value of this? Sigma 1 plus say j omega 1, clear. Say I am also having a point here. So, this will be sigma 1 minus clear. So, this point and this point, what you can say? This point and this point, what you can conclude? Their real value are same, imaginary value are complementary. So, this is conjugate, complex conjugate, right. So, now you say I have a, this is known as the S plane. So, this is right hand S plane, this is left hand S plane, right. So, if it is in the left hand side, these two conjugate poles are left hand side, what will be their value? Say minus sigma 1 plus j omega 1 and minus sigma 1 minus, okay. So, there is a concept of pole and 0. Suppose I have a transfer function. So, what is the root of this equation? S is equal to minus a. So, this is known as the pole, okay. Similarly, suppose I have a S plus a, S minus b. So, this numerator, its solution is S is equal to, this will be known as the 0. So, you know this concept, right. So, if you have a transfer function, the expression of the denominator, their solutions, they are your pole positions, okay. Now, tell me, suppose if this is your expression, okay. In this expression, if this conjugate, they are on the left hand side, what is actually happening in your equation? You have, say, this is one equation, this is one equation, okay. So, you just try to think that as your frequency is changing, what is actually happening? See, in this expression, this is a is minus, right, your solution is negative. So, if this value is increasing, this frequency is omega portion, your frequency and sigma both are increasing, they are increasing in this direction and this direction, and this is actually what the amplitude, you think of amplitude, what is happening, this is getting reduced because it is in the left side. In this equation, you think this is in adding up, right, this is in the right half plane. So, if this sigma is increasing and this omega is increasing, what is happening? You think about the equation, my value is keep on increasing, right. So, from this point, can you tell me in which side, if your roots are, that is by default it should be stable? Left side. Why? You see the its timing diagram, okay. This response of a step input. See, this is dying down. If I have a oscillatory input, this oscillatory input with time will die, because this is the amplitude is falling down by the nature. But if my roots are on the right hand side, with time it can go unstable. What is the meaning? Now next question is, what is the meaning of stability? Do you know the definition of stability? Stability, we can say, suppose we give a bounded input. Bounded input means I have a limit. Positive input must be within this range, negative input must be, for example, op amp. What is your bound? Plus VCC and minus VE. So that is your boundary. So your input should be within that boundary. So when will you say that it is unstable? Either it is going to saturate or crossing, right? So this saturation is possible here. So there is a chance. So if I give a bounded input, in case of if my poles are in negative plane, the chance that it will be within the range is more. So by default we say, if the poles are in negative half of the S plane, this is stable. But in this case, it may happen, positive feedback what it does, keep on increasing, right, and it will go beyond your limit. Okay. With a bounded input you are getting output crossing the boundary. So that is the definition of stability. Clear? So these two conditions we know. There is a third condition, that is called the conditionally stable or marginally stable. Think about oscillator, what it does. It keep on oscillating at a same frequency, it will give you a sine wave. So that happens when your roots are on the imaginary axis, only j omega, there is no real part. So this tends to oscillate, but it is bounded. Okay. So we will study oscillator in details, there we will again discuss this, right. So this is, I just touched a little bit, I am not going into details because this is beyond the scope of this subject, but you will learn this in control theory class. Okay. So because whenever we talk feedback, it is connected with stability. Okay. So stability analysis will be coming with feedback. So you will be again study feedback, not circuit point of view, but you will study again in control theory. This you already have discussed, right. Negative feedback reduce my gain, but increase my bandwidth, right. We discussed this. Previously it was like that. With feedback my gain is reduced, but my bandwidth is increased. How? So you see one interesting point. In open loop your pole position was here. Okay. In open loop your pole position was here. Because I have used the feedback, this is moved to a higher position. What higher position? Multiplied by 1 plus A beta, right. So same thing, you are dividing with something bigger, so your amplitude is falling down, but frequency portion now you see, this is at this frequency it will go to have a 1, right, inverse. What is this? 1 plus S into say 1 plus tau S, right. So tau should be 1 by S. So this inverse is actually getting increased by omega pf, your closed loop bandwidth is increased by 1 plus A beta. So, my gain is reduced, but my frequency is increased, right. We discussed this before with negative feedback, we calculated that, right. We calculated with one transfer function Hs, we put Hs is equal to A by 1 plus A beta, A we put as Am by 1 plus tau into A, something like that, right, and we enlarged the equation, we found that our this corner frequency is increased. The same thing we can explain with pole position, that pole is, because of this feedback, this is moved away. So, same concept in Bode plot, this is our phase, this is amplitude, right. So, we can also have the phase, this is amplitude plot with frequency, and this is phase plot with frequency. Okay. This is known as the Bode plot, that you will also learn in control theory class, Bode plot. So, you can understand that so many subjects are interlinked. Control theory, that we think about the instrumentation subject or related to instrument, but the same control is also related to our circuit, because circuit are also physical element, right. There we also have stability analysis, stability problem. You have designed an amplifier that could be unstable. So, you have to do all the stability analysis. Okay. So, Bode plot is also another tool for analyzing the stability. I am not going into these details, I am just giving you some hints. Can you tell me this thing, what is the slope of this is falling, right. In filter we have saw this response, right. Can you tell me what kind of filter response is this? Low pass filter, low frequency it is passing, at high frequency my gain is falling, right. And what is the slope of this roll off? Minus 20 dB per decade. Where is the pole position? This is our corner frequency, right. This is my pole position. So, this is a single pole or double pole? This is a single pole, that means I have a expression like something like this. Now, if I have two pole, it is falling by 20 dB per decade, after that it will fall another 20 dB. So, what will be my slope? Minus 40 dB per decade, right. Say at that frequency I have a 0, 0 will add up. So, it will again be plus 20, so it will become minus 20, getting my point. So, poles are decreasing my slope, zeros are increasing my slope. So, say let us see this multi-pole system, I have a pole here at this position 20 dB per decade, at this position it add up another pole minus 40 dB per decade, at this another pole minus 60 dB per decade. Suppose at this position instead of a pole, if it was a 0, it will again go up to minus 20. Okay. This is one example I am just telling. Okay. So, we will end our class today up to this. So, what we have learned today? We have learned about negative feedback, 4 kind of amplifiers, voltage amplifiers, current amplifier, transconductance and transresistance. We have seen the input and output impedance, how they are modified by the negative feedback. Then little bit we saw how the stability is modified, right. If the pole position are negative half of the S plane, this is stable, and if it is on the positive half, this is going to unstable, and if it is on the imaginary axis, it is conditionally stable. Thank you.